So that's what went on in the inner solar system. With 90% of the non-solar mass being in Jupiter and Saturn, you wouldn't be surprised to learn that the real action went on in the outer solar system beyond what we call the snow line. The snow line is that line that separates the inner solar system where water was vapor from the outer solar system where water was a solid. Why is this so important? Because those initial solid dust fragments that coalesced chemically to form planetesimals slowly and painstakingly in the inner solar system were very rare. They were made of these trace elements, iron, nickel, aluminum, that are very rare in the solar system. In the outer solar system, water was a solid. Little grains of ice could stick to each other chemically. Water is much more prevalent in the solar nebula and in the solar system today than iron or nickel or aluminum or all of them put together. Despite the smaller overall density at larger radius, the fact that water was available to coalesce as solid particles meant that the whole process of planetesimal and protoplanet formation goes much, much faster. This is especially true right at the snow line, about 5 astronomical units from the sun, and so Jupiter, which lives right at that radius, grows very, very fast. It goes through the initial accretion of planetesimals to protoplanets much, much faster than the inner planets, and reaches very rapidly a mass of 10 to 15 Earth masses. And this is a crucial borderline. What is this object made of? Well, by this time it's certainly spherical, it has melted, it has chemically differentiated. Iron will have dropped into the central core, there will be an outer core of silicates and rocky materials, and then the outer mantle will be water. It was made, much of the planet would have been made of ice. The ice would have melted, so we now have this sort of layered structure with an inner iron core, an outer silicate core, and a watery mantle. And this object, when it reaches 10 to 15 Earth masses, achieves an important milestone besides melting and chemical differentiation, one that the Earth, which never got this big, never had a chance to achieve. At this point, the gravitational attraction of this large object, which has become quite compact under the force of its gravity because it's held up by pressure, is large enough to bind an atmosphere of hydrogen and helium. Now this is a breakthrough because, of course, while water is more prevalent in the solar nebula than nickel, water and nickel together are both trace elements. What the solar nebula is really full of is hydrogen and helium gas. That's 98% of the mass. Once you have an object massive enough and to bind hydrogen and helium, remember we saw that hydrogen and helium are not bound to Earth, but at the lower temperatures in the outer nebula, they will bind to Jupiter. Jupiter is rapidly able to gravitationally attract all of the gas essentially in its vicinity. In fact, one can imagine the formation of Jupiter as a gas giant essentially as a gravitational collapse, a gravitational instability, similar in smaller scale to what happened at the center that produced the protosun. In other words, the dense core that is the core of Jupiter forms an instability, causes a chunk of the gaseous disk to collapse onto that core. What does this produce? Well, it produces the usual phenomena. It produces increased angular velocity as the gas collapses. We find that the rotation speeds up. Indeed, Jupiter rotates about its axis once every 9 hours. A giant object like Jupiter, indeed, spins much faster than Earth does. In addition, this causes the flattening into a disk, just as the solar system flattened into a disk. So we get the phenomenon around Jupiter of an accretion disk, which is the place from which gas is falling onto the nascent planet. And in that disk, some of the material, because of the centrifugal barrier, will not fall onto Jupiter. Some of it will be icy. And we have, as with the inner solar system, we had the formation of planets. Here the leftovers will form moons. And as we'll see, closer to the planet rings. And so these structures in the equatorial plane of Jupiter are just mimicking on a smaller scale the entire planetary system that lives on the equatorial plane of the sun. It's the same issue of a cloud collapsing, spinning up, and flattening. In addition, of course, the core is heated by Kelvin-Helmholtz heating, but we have a rapid runaway growth, especially towards the end. It takes about 10 million years, coincidentally a very good time scale, because that's when the gas gets blown away by the sun, for Jupiter to accrete roughly its current mass, and over the same time, it essentially exhausts all the available gas near its orbit. So whereas Earth was able to trap all the planetesimal matter, but the gas was essentially unbound, and the inner nebula was still full of hydrogen and helium gas until the T-Tauri wind blew it away, and the outer nebula, before the T-Tauri wind cleans up, Jupiter and Saturn have essentially sucked up all the gas in their orbits. Now, Saturn is not as massive as Jupiter. Well, Saturn is a little farther out. The density is smaller there. There is less water. Saturn accretes to critical helium and hydrogen binding mass a little bit later. The density is also smaller, but mostly it starts later. It has less time. There's less gas left. And so Saturn never quite attains the dimensions of Jupiter, but it repeats the same process. Gravitational instability, collapse of a cloud, speeding up of the rotation, flattening out of an accretion disk, and moons in the equatorial plane. So Jupiter and Saturn live the rich life outside the snow line, and so become fat and big. What about Uranus and Neptune? Well, those are qualitatively different objects. They're giants on terrestrial scale. They're not as big as Jupiter and Saturn, and they're not predominantly hydrogen. Despite what we might have heard, they're predominantly ices. Each of them has only about a Earth mass of hydrogen bound to it. Presumably, they started yet later. There was not much gas left. But even so, we have a problem. In their current orbits, there is no way that the modeling tells us that these planets would have grown in time to bind any hydrogen at all in the time before the sun blew the hydrogen away. What must have happened is that they must have formed closer to the sun, where the nebula was denser, and then migrated out. Migrated out? I thought that we solved Newton's equations, and they told us that an object orbiting the sun will move in a closed orbit, which is an ellipse. Newton solved his equations. He solved them correctly. What is this migrating? Why would something move in an orbit that is not an ellipse? This is an important topic, so let's pay attention to it. So, indeed, the motion of an object around the sun, or in fact, the slightly more complicated problem of two objects orbiting each other, is a problem that physics students solve in their first or second year of doing physics. And it's completely solved, and the solutions are ellipses, or hyperbolas if the motion is not bound, but we know how to solve that problem. Things become complicated when you have not one planet orbiting the sun, but say two planets orbiting the sun, and you want to take into account not only the gravitational attraction of the sun on each of these objects, but also the gravitational attraction of one upon the other. This brings you into the 3 or 4 or whatever body problem, and the 3-body problem in Newtonian physics is not a freshman exercise. In fact, it's not solved, and in some technical sense not analytically solvable, because the problem has a property called chaos. It is the fact that small infinitesimal changes in these initial conditions, where and with what velocity you start the objects out, can lead to qualitatively different results. And so direct solution is difficult. How do we actually understand what's going to happen in something complicated like the solar system, which is at the very least a 9-body problem? Well, one possibility is we numerically simulate the problem. In other words, we run through the exercise that I described at the end of our Newton's laws discussion. We start with the initial positions and velocities, we compute an acceleration, figure out from that where things will be a few years hence, recalculate the forces, recalculate the accelerations, and basically go through that process on a computer. It's difficult, but it's doable. That's how we know what the solar system will do billions of years hence and what it did billions of years ago. But under some circumstances, it's useful to think, well, under most circumstances, the gravitational force of the sun dominates gravity in the solar system simply because the sun is so much massive than everybody else. This might not be true when two objects come very near to each other, so certainly the dominant gravitational force acting on me right now is that of the Earth, not of the sun. Despite the sun being more massive, the Earth is much closer. So if two objects are moving in solar orbits but then approach each other very close, what I can do is sort of stitched together approximations. As long as they're far enough apart, I'm going to ignore their gravitational attraction on each other. When they get close, then for an instant I'm going to forget about the sun and let them collide with each other and only treat the gravitational attraction between them. And then once they've moved far apart again, they will have new, changed velocities. I will plug those into the equations for solar orbits, and essentially the objects will have transitioned through the collision from one solar orbit to a new solar orbit. And this process goes under many names: gravitational slingshot, gravity assist. It's often used by NASA to propel its spacecraft to higher orbits. This is how Voyager got to leave the solar system. It's how Galileo got to travel as far as Jupiter. And the way it works is that if you take into account that the scattering process, the collision is with the gravitational collision, is with a moving planet, and you adjust the initial conditions right, you can set it up so that in the process of collision, the lighter object, in this case, say the spacecraft, picks up some extra orbital velocity from the moving planet. And here is, for example, a demonstration. This is the trajectory of the Dawn craft, whose image is of Vesta, the asteroid we were looking at before. This was launched from Earth on one of those Hohmann transfer, those elliptical orbits we talked about, such that almost at the antipodal point, it was meeting up with Mars. And then it wasn't quite antipodal, it didn't go into Mars orbit, but as it zoomed past Mars, Mars accelerated it. And then, of course, as it passed Mars, Mars slowed it down. The net effect, though, because Mars is moving, is that it acquired some extra energy from the collision with Mars, went from one solar orbit into a new solar orbit, and the design of the orbit was such, this was precisely a minimum energy trajectory to the orbit with which we wanted it to arrive, which is Vesta's orbit out here at a larger distance from the Sun. And it arrived and then slowed down and orbited along with Vesta, fell into orbit around Vesta. This is an object of careful design, and there it took those beautiful images. And when it leaves Vesta, it will hop up to the orbit of Ceres, another asteroid, and will take images of Ceres. And so this gravity assist is nothing new. This perturbative approximation works well when the objects encounter each other once and then are now not any very close in the future, because Dawn is now in Vesta orbit and will not get close to Mars in the future. It looks different when this situation is that two objects are in closed orbits around the Sun, and so will be at a nearest approach every time their orbital periods coincide. We'll see that in a moment in this nice demonstration, and maybe that'll clarify the situation. So, this is our old planetary configurations simulator, which I'm going to repurpose to a different goal. So imagine that we have two planets, both orbiting the Sun in initially circular orbits. I'm going to start, as always, when the two planets are in opposition or conjunction or whatever you want to call it, but they're lined up with the Sun. This is the moment of their closest approach. At this point, what is going on? Well, there's an attraction, and as the inner planet has been catching up with the outer planet, the gravitational attraction between them has been attempting to distort the inner orbit this way, because the inner planet is attracted to the outer planet, so it acquires a slightly higher velocity. At the same time, it's slowing down the orbit of the outer planet, and so the outer planet's orbit is being distorted slightly in this direction. And of course, I grossly exaggerate what is going on. Now, what I'm going to do now is allow the animation to run for a bit, and we'll see that after a while, as usual, the inner planet outruns the outer planet, and if we wait long enough, they come into conjunction again about here. Well, this time, again, in conjunction, there's a distortion of the orbit. The inner orbit is being distorted in this direction, while the outer orbit is being distorted in that direction. And you can see that we can do one more round of this crazy race, and what is going to happen is that they will come into conjunction again at some other position along their orbits, And I've got it timed so it's kind of close to where it was before, but not too close. This time, the inner orbit is being distorted into this shape, and again, I am grossly exaggerating, and the outer orbit into the perpendicular shape, something like this. You see that what's going on is that the net result of all these deformations is not going to be very much, because at each conjunction, the orbit is deformed in a different direction. Aha. Now, I'm going to try the same thing, except I'm going to set up the ratio of the radii of the two planets to be 1 to 1.59. If you check with Kepler's laws, this will make the ratio of their periods 1 to 2. And we'll see that this changes things considerably. What's going on here, again, during this conjunction, the inner orbit is being stretched out in this direction, while the outer orbit is being stretched out that way. And now, if we let the animation run, we'll see that because the ratio of the orbits is 2, the next conjunction will happen precisely after the gray, slower outer planet has completed 1 rotation and the inner planet has completed 2. And guess what? The deformation of the orbits this time is in the same direction. What happens this time is that at each encounter, the orbit is further deformed in the same direction. When you have orbital periods, this was the situation when P2 was 2P1. When the ratio of the periods is a fraction with small numerator and denominator, we'll get once every denominator number of periods, a conjunction which extends the orbit in the same direction, and the orbit over time will become more and more deformed. This is called orbital resonance. What we saw there is this phenomenon called orbital resonance. From a distance, the gravitational interaction between two planets might perturb their orbits slightly. If the periods of the solar orbits are resonant, what does resonant mean? That means that NP1 is MP2, where N and M are sufficiently small integers, because this means that if P2 is the larger orbit, so that N is the larger number, every N orbits of this one, conjunction happens at exactly the same place. And so every N orbits, the effect is enhanced. If N is not too large, then we get this resonant perturbation, and the net result is that the orbit will be elongated in a particular direction. And notice that as it's elongated in that direction, the distance of closest approach only gets closer, and so this again is a nonlinear process that can continue, and so successive perturbations add. Now there's 2 things that can happen, and the details of that dynamic is beyond the kind of math that we're going to do. One possibility is you get metastable resonances, not quite stable orbits that can go on forever, but orbits in which 2 things can continually orbit for a long time, and a great example of that is Earth's most famous other moon. It's named Chrithni, or whatever the pronunciation is, and it actually orbits the Sun in a solar orbit that is in 1-to-1 resonance with that of the Earth. The objects will never collide, the orbits are tilted, and the timing is off, but what happens is that Chrithni orbits in a more elliptical orbit than the Earth does, but its period is precisely 1-to-1. You will see that every time the 2 objects arrive at this sort of intersection from our point of view in right ascension of the orbits, they arrive there in precisely the same configuration. This is orbital locking or resonance, and what this looks like from Earth is, if you imagine fixing the Earth in one place, so this is the Sun, the slight wiggle in the Earth's orbit about the Sun is due to the ellipticity of the Earth's orbit, and here's Corinthi orbiting the Sun, but as we see it from Earth, Corinthi goes around a sort of bean-shaped orbit. This is often very confusing. People describe this bean-shaped orbit and try to figure out why anything would orbit the Sun in a bean-shaped orbit. It looks to us as though Corinthi is orbiting the Sun in a bean-shaped orbit. That is really just the point of view from Earth because we're moving along our orbit. And indeed, there are 3 or 4 other objects that are locked into resonant orbits with Earth. And so we have more than one sort of moon, but only one that is both naked eye visible and actually in Earth orbit. But this is sort of a bound orbit between the Earth and the Sun. We're together controlling the motion of this piece of rock, Corinth, which is also quite small. This is not the standard outcome of orbital resonance. Typically what happens in orbital resonance is that because the orbit is deformed in a coherent way in a particular direction, the entire situation, and because of this nonlinearity, the entire situation becomes unstable and the orbit is destabilized. This is probably best characterized in the asteroid belt. The asteroid belt, remember, lies between 2 to 4 astronomical units from the Sun, and in this region fall all of the resonances with small numbers of periods with Jupiter and with Saturn. And what we observe, indeed, this is the distribution of asteroids as a function of their distance from the Sun. And so this is the position of Jupiter. The fact that there are asteroids in Jupiter's orbit, that's a resonant situation. Those are those Trojans. In fact, how those Trojans fall into a stable resonance is again something that's a little bit beyond us, but there are these Lagrange points around which there's an unstable resonance, and these asteroids orbit that unstable position, and so they end up being locked for long terms into these positions 60 degrees away from the planet along its orbit. But more importantly, in the more inner reaches, this is the main asteroid belt, over here is Earth orbit, and what we see is that there's a distribution of asteroids and then there are gaps. There are distances from the Sun at which nothing orbits. These are called Kirkwood gaps, and what they correspond to is distances from the Sun at which the period of an asteroid, were it to orbit there, would be a third or a half or 2/5 and so on of the period of Jupiter. These are objects which would be coming into orbital resonance with Jupiter. That would distort their orbits into eccentric orbits, and if there were a little bit of a tilt to their orbit, that too would get accentuated, and eventually they get completely ejected from the asteroid belt. So nothing orbits at these orbits, and in particular, not only are these guys, is there nothing orbiting there now, but in the original asteroid belt, as Jupiter and Saturn were forming, they started to distort the motion of things in the asteroid belt. This led to these objects not moving in the nice circular orbits into which everybody was trying to settle, but into these eccentric orbits. This leads to violent disruptive collisions between the asteroids, or the planetesimals and protoplanets that are forming in the asteroid belt. This is one of the ingredients into why a planet never managed to form. The larger objects were colliding destructively at high speed, rather than sort of overtaking each other very slowly with slow relative velocities, as was the case in the inner solar system, farther from Jupiter. And this process of resonant emptying of the asteroid belt eliminates most of the stuff that was there. Astronomers estimate that there were between 1 and 3 Earth masses of material in the region from the Sun between 2 and 4 astronomical units, and most of that has gotten kicked out. Less than 0.1% is now present, and we attribute this to the gravitational effects of Jupiter and partially Saturn. Now that we understand that orbits can change, we can understand something about the currently accepted, and I should say it's relatively recent and might still change, understanding of the early evolution of the relevant part of the solar system, namely the outer solar system. This is called the Nice model. It was formulated in a sequence of papers that came out at the University of Nice. These were where the simulations were done. And the idea is this. Remember, out at 30 astronomical units where Neptune orbits today, there is no way to form a giant. In this model, the 4 giants form at distances between 5 or slightly away from where Jupiter is today, 5.5 astronomical units, out to 17 astronomical units, so closer in than they are today. And here 4 giant planets form, and they completely exhaust the gas in the disk. Beyond this orbit, all the way out to 35 astronomical units, planetesimals have formed. There are ices, methane, water, farther out even more. and they do form planetesimals. And so there's about 35 Earth masses worth of planetesimals in a disk outside the orbits of these giants. Now, over time, the outer giants, it seems that probably Uranus was formed farther from the sun than Neptune, and they crossed. So Uranus will encounter some of the inner part of this disk. So when Uranus, which is in an inner orbit, meets these fragments in the outside of the disk, then it slows them down, and Uranus slows down the fragments, shifting them inwards, and acquiring a little bit of their energy, it shifts slowly outwards. Now this is a very slow process because planetesimals relative to Uranus's orbit doesn't change much, but there's this constant rain of planetesimals moving inward, propelled by collisions with the outer giants, where they encounter Uranus, and then next they encounter Neptune, and next they encounter Saturn, and eventually they encounter Jupiter. And this slowly shifts the giants outer. Over millions of years, all of these giant orbits are slightly growing. Now, this is very slow until after about 600 million years, something happens. And what happens is that this motion brings Jupiter and Saturn, who are not too far from that right now, into a 2-to-1 orbital resonance where the period of Saturn is precisely twice the period of Jupiter. At this point, we have the problem that we discussed. There's this instability. The orbits are both elongated, one in orthogonal directions, in a coherent way, but these are two massive objects. The gravitational impact on each other is non-trivial. They both get deformed into eccentric orbits. That in turn influences the rest of the giants. And what one sees in the simulations, and you can, I'll post a link and you can see these simulations yourself, is that once this point is reached, then very rapidly the planetary orbits change, and Uranus and Neptune swap places and get pushed farther out. Jupiter gets moved a little bit inwards as a result of all of this, and in the process, the entire outer asteroid belt is depleted. All of those planetesimals beyond the disk are scattered either into higher orbit, trans-Neptunian orbits, beyond 30 astronomical units where Neptune today resides, and they form what we think of now as the Kuiper belt, or some of them are ejected into very eccentric, off-axis, off-plane trajectories, and we think of that as the origin of what we now see as the Oort cloud. And notice that as Jupiter and Saturn are moving resonantly, they apply a resonant and shifting influence on the asteroid belt, and this really is what completely depletes it and prevents the formation of anything there. Also, the nearest planet to this whole mess is Mars, and the perturbations applied by Jupiter and Saturn to the orbit of Mars are what prevent, we think, Mars from becoming a planet the size or mass of Venus or the Earth. The main difference is that it was subject to more perturbations as it was trying to grow. Moreover, following this the resonant period, Saturn moves out. It collides in the sense of orbital encounter with Uranus and Neptune, pushing them out into eccentric orbits. They encounter the planetesimals, as I said, destroying the disk, scattering things into either trans-Neptunian orbits or higher orbits. Some of the planetesimals that they encounter are in fact slowed, and if they're slowed down sufficiently, they rain down into the interior solar system. This means that there will be a time period in the history of the inner solar system, a time, and the outer solar system actually, where there will be this barrage of things coming from this outer disk of planetesimals and raining down all the way down into the inner solar system. This period, and we see its traces in the history of cratering in the inner solar system, is called the time of heavy bombardment. And when we talk about cratering in the inner solar system and on moons, we will be able to trace a timeline that matches up with this. And then the remnants of the disk create enough friction to settle everything down into the circular orbits, which are essentially stable, in which we find them today. So here's a graphic representation. We start out with the four giants note that light blue Uranus is farther out than dark blue Neptune, and then Jupiter and Saturn are inside them. After a few 100 million years, just before the resonance, the orbits have shifted. They're a little bit more eccentric. Neptune and Uranus have exchanged places, and Neptune is starting to plow through this disk of planetesimals, and indeed the disk is thinning out on the inside, and some of these planetesimals are being blown down into the inner solar system. Some are being scattered out into the outskirts of the disk, and then very rapidly, once resonance is achieved, the disk is completely emptied. We see a scattering of population beyond Neptune's orbit. Some of them have been scattered entirely out of the plane to form the Oort cloud, and the giants have settled into their accepted orbits that we've seen today. And this is what our models predict was the history of the solar system. This is how we got to where we are. We've answered, at some level, the last question we asked, where it all came from and when. And in the process, we've learned something about how orbits change, though we haven't addressed the question of will planetary orbits change in the future. I can tell you that the solar system is stable on timescales of hundreds of millions of years, at least as far as the planets are concerned. What happens after a few 100 million years, it is hard to predict. But as we'll see, there are other issues that are going on in the solar system on those timescales. We know why there's no planets where the asteroids are. We understand why there are two kinds of planets. We know why the asteroids didn't form a planet. We know why things are round and why some things aren't. And we understand why all planetary orbits are circular and in a plane. Friction slowed them down to circles. The plane is the original plane of the rotation of the solar nebula. And comets move on whatever orbits they happen to have been thrown into, because they are the result of some near collision with a heavy object of some old planetesimal. So we've made some progress, though there are still questions we need to ask. It might be a good time to summarize what we've learned about the history of the solar system with a timeline. So we started our clocks at what I called time zero, 4.56 billion years ago. Something triggers the collapse of the molecular cloud that will form the solar nebula. Within 100,000 years in the inner solar system and less in the outer solar system, we have planetesimals. Within 10 million years, the inner system has formed protoplanets and is beginning to start the accretion of planets. The outer planets by this time are pretty much formed. The T-Tauri winds start to sweep away the gas and the dust, leaving planetesimals that are more massive and dense objects. And so the inner planets take about till 100 million years from this event to completed their formation and settled into their orbits. This includes the massive impacts that formed the moon and stripped Mercury of its outer layers and so on. After about 600 million years, we hit the Jupiter-Saturn resonance. And this is the time that the asteroid belt is depleted, the outer planets migrate out pretty much to their current orbits, and in the process, some of the material from the planetesimals beyond Neptune's orbit gets ejected out into the Kuiper belt, some into off-axis orbit, off-plane orbits, producing the Oort cloud farther out, and a lot gets thrust into the inner solar system, and we find the period of heavy bombardment. So we should expect lots of 3.8 billion year old cratering, right? Because that is the time of the heavy bombardment. And by about 700 million years, the stable configuration has basically been achieved. Planets exist with roughly their current mass in pretty much their current orbits, and not coincidentally, the first signs of life appear on the planet we call Earth.